Capacitance stuff. I'll quickly review those principal properties, and then I'm gonna knock out a couple of problems for you. I haven't worked through that stuff. Yeah, okay. A couple capacitors in series. So the series, what is the rules were, so in series, the charge is the same, the voltage is different, and the capacitance adds capacitance adds, I guess reciprocally, right? Yeah. Okay. So for series combination, you got this is the equation that I use. Q1 equals Q2 equals Q equivalent equals Q. Charge is the same. Voltage is different, so V equivalent equals delta V equivalent equals delta V1.
Professor, could you move
Yes,
the camera a little bit to the left, please? So sorry about that.
that's all right. You good?
All right, that looks
Okay.
perfect. Yeah, looks great. Thank you.
Okay. Yeah. Got it. Plus delta V2. And the capacitance adds reciprocally. So it's like, the 1 over C equivalent equals 1 over C1 plus 1 over C2. But I like to write it like this, that C equivalent equals the reciprocal of the reciprocal sums. So those are the properties for series. And for parallel combinations, you have that the charge is the same, so Q equivalent equals Q1 plus Q2. So I guess you could write Q equivalent equals the summation I equals 1 to n of Q sub i's. The voltage adds reciprocally. I'm sorry, the voltage is the same. So delta V equivalent equals delta V1 equals delta V2. And the capacitance just adds, so C equivalent equals the summation on the end of C sub i's. So we talked about all of that at length on the other day. So let's work through an example or two. Then I'll give you 2 or 3 to work out. So say we have a battery and like so, and 2 capacitors in parallel, in series, sorry, like that. So the idea is to find, for all problems like this, the objective is to determine the equivalent capacitance and the charge on each capacitor. So find CEQ, and then find the Q sub i's. So we'll have like a 5 microfarad capacitor So the battery will be 8 delta V equals 8.0 volts. This will be 5.0 microfarads and 7.0 microfarads. So note the significant digits to sig dig. So how do you work out something like this? Well, the first thing you want to do is find the equivalent circuit. You always, and I know it's going to, now here, I'm going to give you this warning once, twice, 3 times throughout this next few minutes. And you probably won't do it, or something. Statistically, students try to take shortcuts. Where you do it in your head, but I would suggest redrawing the circuit every time you have to add something. And then once you get to equivalent capacitance, then you backtrack doing the finding the charge. I'll show what I mean as we move along. You'll see what I mean. So we're going to combine the equivalent capacitance of these two. And for this guy, they're in series, right? Because you can tell because the charge is going to be the same. So if they're in series, you have to add the capacitance like this. But I'm going to redraw it anyway. So the equivalent capacitor circuit is going to look something like this, just going to have to rejoin. When I redraw the equivalent capacitance between those two, polarities around. Doesn't really matter in this case, but you get equivalent circuit looks like that. So 8.0 volts, and I always do like an arrow from which one goes to which in my notes. And in this guy, the best way to add this, this is the way I do it. And I like it like this because this is literally with the scientific calculator, this is how I put it in. So I've got 5 and 7. So the problem we're actually calculating is this equivalent capacitance will be like 1 over 5.0 microfarads plus 1 over 7.0 microfarads. And then once you add those, you take the reciprocal again, and that will give you the answer. So 5 E6 negative. Reciprocal, and that's what I do. I put in 5, take a reciprocal, put it in, well, yeah, I have a HP, but whatever, however you put it in, and then you add them. So 7 E6 negative. So that's 2.9. You want to store all this stuff too. Remember, don't truncate, right? So I'm going to store that in the register. So this equivalence, this capacitor is 2.92 microfarads. So that's one solution. And now I have to get the charge on each of these initial capacitors. So now you have to work backwards. Remember, you're always using the get the charge, the voltage and the capacitance of this equivalent circuit. So you get the charge on the equivalent capacitor using the definition of capacitance, right? C is equal to Q over delta V. So in this case, I would have to solve that for delta V. Solve for this guy, then solve it for Q. So the Q equivalent in this case is going to equal to C equivalent times delta V. So that's going to be the 2.92 microfarads times 8 volts. In this case, just multiply by 8. So, so that looks like that's like 2.33 times 10 to the negative 5th farads. Now, for capacitors in parallel, the charge splits. It's inherently different. So the charge of each of these 2 microfarad, these 2 capacitors have to add to be the charge on this guy. So this 2.92 microfarads is going to split between those two capacitors. Now, here's the thing. You know, what this implies, I didn't write the quantitative description, but the wording I used for the charge is that the charge is inherently different on capacitors in series. Excuse me. Sorry, what am I saying? I'm in my head all messed up. That's the opposite. This is in series, so we're over here. So the charge does not split. The charge is the same on each of these capacitors. Remember that? We had that long discussion. I had to break through because I finally figured out why, because it's so counterintuitive. And I'll go through that again really quickly. So let me just say that I just had a brain fart. I was applying the parallel combination to this guy because it was just right in front of my face. So no, this is not in parallel. Everything we've done is right so far. We've got the charge on the equivalent capacitor, but now we have to figure out what happens between these two. And what happens is that it's this rule. So the charge on each of these capacitors is the same, and it is the same as the charge on the equivalent capacitor. Okay, and so that's the answer. That is the Q1 and Q2 is equal Q5. I call it Q5 and Q7. Q5 equals Q7 equals Q equivalent, which is just 2.33 times 10 to the negative fifth farads. And yeah. No, that's it. It's coulombs that we're going through. This is coulombs. Sorry, coulombs. Microcoulombs. Right? Oh yeah, right. Yeah, right. Now, I just want to talk about that because I'm just so proud of myself for having. Can anyone describe? Can anyone quickly tell me why? What we had? What's the justification for it? Because you see what I mean, right? It looks like really counterintuitive. Like, why would it be the same? Does anyone remember the argument that we came up with? Am I the only one that's counterintuitive? Or like, doesn't that look a little funky? Like, you get this guy, but then it's just actually it's literally the same as on both of those. Hello?
I think from what we talked about last time, it was the fact that it was the lack of electrons on one plate leading to the accumulation of charge in the other plate, and there being a finite number in the system in the beginning, meaning that with regardless of the number of capacitors in the system, the charge number quantity-wise will not change. That's what I remember you explained about.
Oh, okay. You're kind of, yeah. I mean, it may be that you do it exactly understand, but the way you're saying it doesn't fully nail it for me. But yeah, very, very, very warm. Daniel, you want to follow up and respond? Yeah, so yeah, you're about to respond.
That's what I also remember from last lecture. Uh, but yeah, that's what I remember. But I really don't know how to word it. I feel like he probably worded it better than I would have. But yeah, I do remember us talking about
Okay.
the way charge moves and or flows through, and how it accumulates on one plate, not on the other. And yeah, I forget
Okay.
where to go from there.
Okay. Okay. Fair enough. You get both of you get half credit. If that were a question, at least maybe a little bit more than half credit. On a 5-point problem, maybe I'll give you 3 points for that. Julia, anybody? Julia, yeah. You want to respond? Because I think if I remember correctly, it might have been you who prompted the. I don't know. Someone asked a couple questions that kind of got me on that track. Anybody? I don't want to put you in the spot, Julia, if you don't want. Rick? Louis? Anybody else? All right. Yeah, so I guess the simplest way is that there is the only excess charge that resides. So stored charge on a capacitor is only going to be, the sound is choppy. Let's make sure it's on. Signal might be a little bit weak. No Wi-Fi is on. Just making sure about that. The only excess charge, this stored charge in a capacitor is only going to be excess charge. And if you go through our argument for how charge, stores, put it off one plate, like in this case, the electrons come around and they're stored on that plate there, on the back plate here. And when you put more than one capacitor in, that's still the same case. Charge comes from this side of this capacitor, and the excess charge, electrons are actually stored on this plate right here. That's the only guy that gets excess charge. Now, what happens is, because of the interaction with the field, and because between the capacitor here and the interaction of the field inside the wire, all of these other three plates, both plates on this guy, and the left plate on this capacitor, what you get is free charge that kind of behaves, it raises to the surface and acts like excess charge because it's being attracted by the fields, the respective fields between the capacitor plates and the wire here. So you do have what looks like is equal charge on the surface. So here you have a negative that's equal to that guy, and of course over here there's going to be positive charge, right? But the positive charge, it's not excess charge that has been deposited on the plate. It's just a free charge within the plate that now behaves like excess charge because the way I see it in my mind is that well, that's not actually true. On this plate, there is actually an absence of negative charge because it's these charges here that will pull it off and take it over the other side. So, but it's still not excess charge, right? There was no excess positive charges put on the thing. It's just that it lost electrons. So that it does actually have exposed positive charge on that plate, but it's still free charge that was in the capacitor or on the plate of the capacitor before all this process started. So it's not excess charge. And the negative charge here is excess charge that's just come to the surface because of the polarized charges on the surface of that plate due to the electric field that arose in that capacitor. And on this guy, the positive charge here is also excess charge, where it's like the atoms, because the free charge of the atoms have kind of shifted away. So I guess it's two different things, right? That's actually polarized. They're both polarized, I guess, because you pull off the electrons here. But it could pull off free charge. So I think it might be over here. You're not actually pulling electrons from the atoms. You're pulling free charge out of that material. So these positive charges here, I wouldn't say that they're polarized electrons. I would say that it's the fact that the electrons have left that material and deposited over here that you get, the I guess the positive charges would still be the atoms, but it's not necessarily because they're polarized. I don't think. I guess, or maybe that would be, since I don't know, it's hard to visualize what would be happening there. But anyway, the point I'm making is that the only excess charge on any of these four plates is going to be the negative charge that was deposited over here. So that's why when you add up all the excess charge on all the plates, you just get Q, right? The same as what you would get if it were just one capacitor. So I know that's a lot of words. Maybe if you were to make a concise statement, you would say that the charge is the same on each individual capacitor because the only excess charge is counted as stored charge. And the only excess charge that exists between the series combination is, the excess charge that was deposited on one of the plates of those series capacitors. I don't know, something like that, or maybe even just only excess charge is counted as free charge.
Professor,
And the excess charge on the series combination is the same. Yes.
on the left plate with
Yes.
5 microfarad, no excess charge on that plate. There are no excess negative,
No,
excess
there's
electrons
no.
on it. Okay, got you. I think I did
There are
not
no
get that
excess
part
electrons.
before.
No.
Got it. Okay, makes sense.
Yeah. So what happens is when you pull those electrons off, you start to get what looks like positive charge on that plate because there is a, because it's the metal has lost electrons. So when that happens, you start to now get a field between the plates, right? Because those charges they have a collective field, and the field is going to point from across the capacitor like that. But when it does that, now these atoms on that plate, they see an electric field, so the atoms become polarized. They draw the electron cloud to it, and you get those little fields inside inside the atoms, as I showed you, such that the electrons are exposed. So they're kind of polarized, and they come to the surface and act like free charge. But it really isn't free charge because, it acts like excess charge. And excess charge, is where you actually are putting excess charge on the plates. But it's not excess because, the whole thing is still technically electrically neutral because you didn't add any charges to it. But because there's a field interacting with the surface of that plate, the field has to terminate on something because it can't go inside the metal. So what happens is shielding effect occurs where electrons either free, I guess it would be free electrons actually, I think in this case, it wouldn't be atoms, will come to the surface and on the other side of the thing, they're exposed, whatever, either free electrons or shielding from the atoms itself. Either way, these kind of pop to the surface and act like excess charge when in fact they're just free charge within the metal. So no excess charge on either one of these plates or the left side of that plate. Only the excess charge in this case would be the negative. In the case of this system would be the electrons on the right plate of the 7 microfarad capacitor.
Got it. Thank you.
Okay. Cool. Let's do an easy one for parallel. Then I'm going to give you 3 or 4 you can do stuff with. So I'm going to go ahead and erase these things. This properties. I want to get those down. I'm so proud of myself. Physics is like that. I don't know if it's like music. Anybody, any musicians or anybody into music? I think I asked Daniel, who plays guitar? Somebody, was it Julia? You play? Play piano. You play? Yeah, play. It's piano, right, Julia? Yes, yeah. So this is the first time you didn't have me for 37. This is the first class. Maybe I asked you that earlier. I don't know why I knew that. Or maybe I'm projecting for some other student. But this is the first class you've had. Right?
Yes.
We haven't had this. Did we have this discussion before about music? No.
Maybe, but like very early on in the semester.
Yeah, in the semester.
Probably.
Yeah. So yeah. So it's like physics is really it's kind of like music in that if you play music you can get to a point. There's always another level you can go if you kind of, I don't even want to term push, but you can always explore different types of music or more complex songs or learn new things about the songs in different ways, different arrangements. You could do that, but there's kind of be like a motivation to do that. because you can always get to a certain level and then you can just stay at that level for the rest of your life, right? If you don't always kind of try to investigate more or find out more things. Well, physics is like that as well, right? You can get really good at certain things and then just never beyond that, or never try to have new explanations or different perspectives. And sometimes it's just difficult. It takes a while for you to be able to see something differently. And for me, I think I mentioned it in the class. I always say it. Like when I got to that, I think I said that there was always this. I just feel like I could explain it, because you're not going to see this explanation anywhere. I guarantee you. You will not see it in any book or anything. All this thing that I just told you, that's me. I just made it up. Not made it up, but I mean, like, and that's the problem. I have looked. I have never seen the explanation anywhere in any book. I don't care how good it is. It'll just say some mess that just doesn't really make sense to me. I call it mess because I don't know. I think people aren't really. I think whoever wrote it they're having the same issue. They're just kind of not saying that. But and it's been like 30 years I've been doing this or whatever. Like, and but then it just I don't know. Maybe that was my lucky day the other day. But I think that's a reasonable explanation. And that's kind of how physics is. Like if there's something you feel like shaky on, or you have a feeling about it, even if like studying for a test or something like that, the best thing you can do is get to a comfortable place where whatever you do know about it, but then also acknowledge that there's certain aspects of the thing. Like I think it's important not to hide behind the fact that you don't know it. Like you want to put it in an organized fashion, but just have a little kernel of awareness that there's something about it. And for me, like, how do I want to say this? It's like the explanation that I was giving all these years is good enough, because no book actually goes beyond the issue that I kind of had about it. But it's kind of like there's a little feeling inside that something's not right. It's kind of like the feeling you have when you leave your key somewhere, or you leave, like there's just something like not right about this. That's the feeling I always had about the explanation about why charge is not the same. And the reason is because I actually hadn't worked it through for myself. And if you work it through for yourself, you might actually come up with a different point of view than what actually is in a book somewhere. And that might be a good thing, because, maybe no one's ever thought about it. I mean, that's how you come up with new stuff, come up with new theories or new explanations for things because not everything, there's a whole gazillion bunch of stuff that we don't actually know, but people don't actually say it because, whatever, unless it comes to be a problem like coronavirus or something like that, So I just want to put that out there, that you want to kind of know what you know, have it organized as you can, and know how it applies to all the different things that people have worked out. But if there's a little something, a feeling or something, that might be because not only you don't understand it, but no one else has understood it. And just that there's no explanation about it because there was no reason to explain it, because we worked around it as a society or as a scientific community and found that, you know what I mean? But there might be a point where we come up against something where we need to figure that thing out, So anyway, so this so far. Let's move it along. We've got two capacitors in parallel. So 7 microfarads and 5 microfarads again. And we'll see how it changes, right? Same battery, 8.0 volt. But how is their stored change and placed in a different configuration? So, yeah, so we'll make this one 5. This guy is 7. Okay. So remember the rules. Voltage is going to be the same. Right off the bat, the voltage across this guy is 8 volts. So you can calculate it. You could actually get the charge, but I just do that first just to kind of keep a consistent with what we did before. And it's just as easy, you know, like the capacitance just adds, right? It just adds straight out. So the total capacitance for that should be what's 7 plus 5? Is that oh my gosh, embarrassing. 12. So yeah, 7 plus 5 is 12, right? So 12 microfarads should be the equivalent capacitance for that guy. So CEQ is equal to 12 microfarads. And the voltage, so Q5 is going to be equal to, it's still this formula here. So it's going to be 5 microfarads times the 8 volts. So what is that? 5 times this one, 40. 40 microcoulombs. Yeah, 40. That's a little bit of a dilemma because I should only write it as 2 significant digits, right? So actually, that's the question about the putting it in. Because you don't write 40 in a point. But if I write 40.0, that's actually, oh, what's the rule? Oh, that's 3 significant digits when you write a decimal. So I guess the way you would have to do it is 4.0 times 10 to the negative something negative 7. So 40 times 10. So yeah, 40 times 10 to the negative 6. And if I take it one more, yeah, negative 7 coulombs. So that I can have the 2 significant digits there. And if you're putting it in the book, in the software, it would be 4.0 E negative. Yeah. Yeah. Coulomb. Yeah, a little bit of a dilemma there.
Wait, is that supposed to be the equivalent of 40 times 10 to the negative 6?
No, I just addressed that issue. It's oh, wait a minute. Am I wrong? 4 times. Oh, so it is. Oh, it goes back. So it's 5, right? What am I doing? If you go
Yeah,
to
that's
the
what I think.
negative,
Okay.
yeah, if you, but it is, yeah. So no, it should be 5, right? Is that right? Yeah.
Yeah,
Sorry.
5 would be correct.
So if you go to the left, sorry, yeah. I always mix these. So yeah, going to the left is, going to the right is, whatever. That's the answer. Yeah, and for the other one, it's 35, right? It's 42. 7 times 8 is, no, what's 7 times 8? 56. So it would be 5.6 times e to the negative 5 coulomb. So 7.0 microfarads times 8. Sometimes 8 is 56. Yeah, so 5.6 e to the negative 5 coulombs. Now that's pretty straightforward, but what happens is it starts to get a little bit, I don't want to say tricky, it's not tricky, but it starts to get a little bit more complex steps when you start to combine series and parallel combinations. All right, so I built it up for you. I want to build it up for you. So first of all, any questions about any of that before I give you, I want you to work out a few things for yourself. Good. Okay, so let me give you another one here now. I messed this up in my head. Wow, let me around. All right, whatever. We have, so let's call this problem number 3. The battery is 8.0 volts, and the capacitors are going to be 8.0 microfarads, 5.0 microfarads, and 5.0 microfarads. So always, again, in all of these, find the equivalent capacitance and the charge in each capacitor. So that's what we're doing. And then number 4, we will have this thing here, we're going to have 6.0 microfarads, and then 5.0 microfarads, and 4.0. You can see it. We have 3.0 here, and then 2.0 here. And we'll keep the battery at, make it 12 volts this time. Go ahead and work on those. Oh, Lord. I think that was the final thing for capacitors. Going through resistance and resistance. Did dielectrics. This did energy. This did. Okay. So the next thing is, I think most schools have 2 chapters on our resistance. One is going to be resistance and resistivity, and the other will be circuits and stuff. Let's see how I did resistance because they combine. Then you start to combine resistors and capacitors. So you guys are doing here. That's what how the university does. So, potential, and capacitance, and current and resistance is chapter 1. And then the next chapter is going to be, yeah, current, resistance, on the ball, and all that stuff, resistivity, conductivity. And then the next chapter is electromotive force. So that's Kirchhoff's rules and all that. So that's yeah. Let me do Kirchhoff's. And the next chapter is I should put capacitors together. That makes magnetism. Okay. Right. We'll do DC. Yeah, DC circuits with so I will get to the first chapter on resistance today. We're going to finish that today. Most of it. After we do this. And then I'll give us a whole day for electromotive force and circuits. The bulk of that day. A lot in that chapter. Yeah, they have RC circuits and for DC. So just a lot. So we probably won't finish all of that next chapter in one day, but we'll get to the bulk of it. Enough to set us up for about 5 weeks left to get everything else done. So, okay. Any questions about any of this? Should work as much as you can, and then I'm going to go ahead and knock it out for you. And then we'll go on to resistors. Get my tea. We have 9:08, so 20 minutes to the break. All right. One, 2 of these before the break. Take this guy. Yeah, again, I'm very much an advocate of redrawing the these diagrams. So my rule of thumb, I usually try to start as far away from the batteries as I can, just to kind of work back towards it. But that also is not really just a general rule, because I could have a battery over here someplace too. So you just have to kind of work through things individually, as it's no hard and fast rule. You start somewhere. But I would say a voltage analysis first, right? Always do a voltage analysis. Now I've kind of made it easy for you, because I've started off giving you these certain patterns of like geometric patterns of the way the capacitors are in the circuit. So it's kind of easy. We already kind of know what the voltage analysis would be, because just from the patterns I've set up. But as you get more complex circuits or different arrangements, it's not so easy to see that. So you always want to make sure you got that down. And that voltage analysis is the process that we started in the beginning, right? Like, so if I have, you can have symbols for them. Like, so if this is V plus, and that's V minus, then over here, this is going to be V plus. But when I go across this capacitor, this point cannot be V plus anymore. It's got to be something else, because I use some energy, and it's I had to have some energy to get across that if I were a charge or something, right? So, and you don't really get across it, but it loses energy. There's going to be a change in energy per unit charge as you move across that thing, because there's going to be a certain amount of stored energy in that would not be there if the capacitor were not there. So over here, maybe I call that V plus prime. Over here is V minus. So then this is V minus, and this is V minus, right? But since there's no component here, that's also V plus prime. So now, in your mind, when you go through and look at the voltages across the thing, look, this voltage difference is going to be V plus and V plus prime, right? That's the voltage difference there. And this guy is going to be V plus prime and V minus, and this is V plus prime and V minus. So again, you don't have to know the value of the voltages, the actual value. You just need to know the relative value. That's what a voltage analysis does. So because these two voltages have the same voltage drop across them, namely V plus minus V plus prime minus V minus, or whatever the sign is, I guess that would be a positive difference, right? So the point is, the magnitude is the same on each of these. So that means these two are in parallel, because they have the same voltage drop across it. And that voltage drop is different from the voltage drop across this. So this guy is in series with all of that. So if you redraw it, you can redraw it like that to see it. I'm going to first combine these in parallel. And again, with the capacitors in parallel, and you might have to put the rules down like I did, and then kind of, like I'm not a person that's big on memorization. For me, that just doesn't really work so well. I use the term learning it. And the way you learn it is, you go through the steps every time. So you have the pattern, you have the rules down, and then you just work through it. After a while, you realize you just learned it. Because if I try to memorize it, I'll be mixing it up all day long. Like, it just doesn't work for me. But whatever's good for you. And you saw me with the process, right? I did. I wrote it down, but now I've got that picture in my mind of how I wrote it down. And even then, I still am prone to make mistakes, because you saw me almost do that initially when I tried to make the series circuit parallel, right? It's just things like that. So you just know what your strengths and weaknesses are, right? But those are the rules, and you always want to know what the basic rules is, and figure out some way whether you need to write it down or wherever so that you're following those same patterns. And then it just kind of becomes organic as you do it a lot. Anyway, this is parallel combination, parallel capacitors add. So when I redraw the circuit, I'm going to have a circuit that looks something like this. So I have the 8-volt capacitor, 8-volt battery, and then I have the 8 microfarad capacitor, but then this guy is going to be 10 microfarads. And you can see it, and you clearly hear that these guys are in parallel. And you know, the same voltage thing, like, right, if I do the voltage analysis, I'm still consistent with what I drew here, because this is V plus. Then I go across that, that's going to be plus prime, and this is V minus, and that's V minus. And so you can still see that, again, the parallel capacitors, the properties worked out, because the voltage drop across, remember in parallel, the voltage across each capacitor is the same, but it's also the same voltage drop across the equivalent capacitance. This is the equivalent now, right? There's 10-volt capacitor between these two. So I have whatever that is, V prime, V plus prime minus V minus, V plus prime minus V minus, and V plus prime minus V minus. So consistent there. And these guys add, you add reciprocally to get the equivalent resistance or equivalent capacitance here. So the equivalent capacitance for this guy is going to be 1/8 plus 1/10, and take the reciprocal of that. And that value will be 4.44 repeating microfarads is the equivalent capacitance I get for that guy. And the charge, remember, charge is equal to C delta V. So the charge, these are in series, so the charge on each one of those is going to be that times 8. So that's, now I need the charge on each one. Oh, right, so it's going to be easy. So this is C8. That's going to be 3.55 times 10 to the negative 5th. So E negative 5, and that'll be coulombs. Now here's a little trick we can do here. First of all, everybody got that? How I did that and how we got up to there? Professor, could you move the camera to the left a bit? Oh, is that old or is that? Okay. You still, yeah, is that old, an old app question, or is that now? Can anybody see the camera? Can you see the board?
Yeah, it could go a little to the left so we can see the edge of the board.
Hello?
But
Actually, maybe I need to bring this back just a little bit. Maybe that's the problem. Yeah, is that good? Very good.
yeah, looks good.
Okay. So yeah, I was asking any questions. We good on this? How I got to that?
So far, so good.
So for capacitors in series, the charge is the same. Thank you. So on this this combination, this 10 microfarad combination, the charge across that equivalent capacitance is 3.55 times 10 to the negative 5th coulombs. However, with capacitors in parallel, that charge splits. Now, it is literally inherently different charge, because like when the charge is flowing, ultimately what we'll see in a capacitive circuit, ultimately the thing charges up and the current stops. We'll do that. We'll talk about that in a couple of chapters. But remember, even though there is resistance in the circuit, we're not really showing the resistance. We're just talking about capacitors. We'll talk about that later after, you know. But when you have capacitors in a leg or in a whole circuit in each leg, then ultimately all the current is going to stop. And but while it's flowing, it's like the Los Angeles River, right? It's water, right? So it splits. And some charge goes down one leg, so some charge goes down the other leg. And the amount of charge that goes down that is dependent upon the value of the capacitance and the resistance actually in each circuit area. So we just have capacitance, we just say the amount of capacitance of the capacitor. Because you might say, well, and we haven't talked about resistance yet, but capacitors also have something like a resistance. It's called impedance, but it's a term that has the same units as resistance, and it has it's like a resistance. So that impedance is also dependent upon the value of the capacitance. So if you have different capacitance, different capacitance in a leg, then you also have different impedance, and that different impedance will determine how much charge flows down each leg. In this particular case, because I chose the capacitor, so it's literally inherently different charge. That's why I use the word inherent, because it's literally not the same free charge that's depositing on each capacitor. However, when you choose the capacitance to be the same value, then the impedance happens to be the same value in each circuit, and what it will make the charge split evenly in each leg. And so in this case, the same value of the charge is going to deposit on each capacitor, and that's going to be half the value of the total, because we know that the charges add to be the total charge on the equivalent capacitor. So in this case, we know that the charge on each of those 5 microfarad capacitors is just going to be half of the 3.55. And what is that? 7, and I was just 7 repeating, so is it 1.77 repeating? I was about to get that right in my head. I'm terrible with arithmetic. I shouldn't say that though. I'm gonna repeat the negative. Yes, I think that's right. I have to check it. It's embarrassing. Sorry, but it is what it is. Yes. So, and that's for each one.
Wait, so how did you come to the conclusion that it was half of C8?
So remember the rules. The rules are that you have to write them down. For capacitors in parallel, Q total, Q equivalent equals Q1 plus Q2, right? So right, the voltage is the same, delta V equivalent. Equals delta V1 plus delta V2. So equals delta V2. And the capacitance adds. So Q equivalent equals Q1 plus Q2. So these are the rules for parallel. So since this equivalent capacitor is made up of a capacitor Q1 and Q2, where the capacitance is exactly the same on each capacitor, then, and the capacitance essentially is what determines how much charge is deposited on the thing, right? Because here, you know that the voltage is, to do it more formally, you know that the voltage is, the charge is equal to the capacitance times the voltage. But I know that the voltage is the same across each capacitor. That was the first thing that I determined. So in this capacitor, the charge is going to be 5 times, because that's another way I can do it. The charge on this thing has got to be so That would be right. Mentioned it right. Yeah. So, oh right, because the voltage across this is not 8. Yeah. Another way we can do this is the following. Maybe I should do it that way to show you. Yeah. So what I said is that I don't know what this voltage is, Julia. It's not going to be the 8 volts, right? Because I lose some of it right here. But whatever it is, it's the same as on each capacitor. Do you get that? Do you see that? That was Julia talking to. Yeah. So do you see that the voltage across each of these capacitors has to be the same voltage?
Yes, I see that.
Okay. So whatever that voltage is, whenever I multiply that voltage times 5, I'm going to get some value of charge. I guess that's as much as I can say. But if I do that over here, because that has the same voltage, and I chose the capacitance to be the same on this capacitor as this guy, then whatever voltage is across that, when I multiply that times 5, I'm going to get the same value of charge. So from just looking at the definition of capacitance, I at least know that the charge has to be the same on each capacitor. Do you get that? If the voltage drop is the same, then the charge has to be the same. But I also know from the properties that we evaluated in general that the total charge on the equivalent capacitor is going to be the sum of the individual charges on each capacitor. So I know the charge has got to split, and the total amount is 3.55. So how does it split? Well, it just makes sense that if I'm making the capacitors the same value of capacitance, then whatever causes the charge to kind of, then whatever the capacitance that causes the charge to store on one capacitor from a certain capacitance, it must be the same amount on the other one. So ultimately, that means that the charge has to split equally since I only have 2 capacitors. If it were 3 capacitors in parallel of the same capacitance, in a leg from that, then it would have to split in thirds or whatever. Yeah. So that's a quick and dirty way of getting it. Quick and dirty. I don't know. Quick, I don't know how dirty it is. But there is another way, and the other way is to actually work it out specifically. I'll do that right now for you just to show you. So the way to work it out specifically is to figure out how much voltage is actually dropped across each of those, and then plug that into this formula, and that will calculate it directly for me. So how do I do that? It just takes longer, right? So that's why I just did the quick way. But how do I do that? Well, I have to go back and figure out how much voltage drops across this guy. Because remember, we go back to this picture, and in this picture, this is a series combination. So here, the voltage on these capacitors actually adds. So in this picture here, the voltage relationship is at the V equivalent. And I didn't draw the equivalent capacitor for you. I didn't go one further step either. I should have done that. I keep saying that. So the next step is going to be this guy, where I have a capacitor that looks like this. The final equivalent capacitance is this picture. The last picture is always going to be this if you go all the way. And that capacitance is the sum of those two. So that capacitance is this guy where I add them reciprocally. But now here I have 8 volts, and so I drop the voltage across, there's 8 volts that dropped across this thing right here, which means there's 8 volts across each one of each one of these has to add to the 8 volts. So the voltage relationship for these two capacitors as well as the equivalent is the following. The voltage across the equivalent capacitor is equal to the voltage across the 8 volt capacitor plus the voltage across the 8 microfarad capacitor plus the voltage across the 10 microfarad combination there, which means that I can figure out what that voltage is because I know how much charge dropped across it, 3.55. So the voltage across the 8 volt capacitor is going to be, well, actually, let's just do this, because what I really want is the voltage across this, this guy, which is going to be the same as across each one of these. So I can just solve this equation for delta V10. So it's going to be delta V equivalent minus delta V8 equals delta V 10. Delta V equivalent is just the battery, that's 8. So that's 8.0 volts minus, now this guy is, it's I can use the definition of capacitance. It's going to be delta V8 is going to be the charge across the 8 coulomb capacitor divided by its capacitance. I'm just getting that from the formula for capacitance. So that's divided by the 8 microcoulombs. Well, put in C8 equals delta V10. All right, that's just coming from need some space. Do that so efficiently. Well, I'll just do it here. The arrow. That is going to be 8 volts. Get some better pens. So that's going to be the 3, and remember, you want to store that stuff. So that's 3.55, so minus 3.55 E negative 5 divided by the 8 microfarads. And that's going to give me the voltage across that guy, delta V 10. So I have to do it over because I didn't keep it in my calculator. So, man, because I don't want to have round off error. So, because if you do it, it's going to be exact. It's going to give you exact if you're careful. So, to rework this real quick. So, what was it? Total, the equivalent capacitance is going to be so 8. Okay. So store 0. Now to get that charge is so we're here. So that charge is going to be that equivalent capacitance times the voltage, right? Yeah, this guy. So that charge times 8 is 8 volts, right? Yeah. Okay, yeah. So I get this guy, so I'm going to store that in 1. Now I want to use that over here. So that voltage is just going to be, well, it's just that divided by, yeah, that's just coincidentally, I chose that to be 8 microfarads. No, the 8 and 8 is the same. So when you divide that by, so 8E6 negative. Yeah, so now that's going to be the voltage across this thing is actually 4.44 volts. Repeating. So store 2. And when I subtract, so when you look at that equation, you're subtracting 4.44 volts from 8 volts. So 8. So the amount of voltage across this thing, the numbers just worked out that way. Don't let that confuse you, because I chose these the numbers to be the same for the voltage and for that micro. But the voltage across this thing is actually 3.55 repeating volts. That is the voltage across the equivalent capacitor here. 3.55 repeating volts. But voltage across capacitors in parallel are the same, and it's the same as the equivalent capacitance. So this guy has 3.55 volts across it, and this guy has 3.55 volts across it. So when I want to calculate the charge on that individually, I use this formula, and I multiply 3.55 volts times the capacitance that it has, which is 5, so 3.55 volts times 5 microfarads. And that gives me, that's another way to get this 1.77 times 10 to the negative 5th coulombs. And you'll get the same one, obviously, for each one of those. So you can see that's a little bit longer to work out. So if you can use the logic and take a shortcut, like I did initially, then. But you know, again, you might have to work through these things. I've picked problems that are, you know, they're probably the most, how do I say it? Like they're going to have all the basic different combinations where you have to work out all these little details. Now you can get more complex circuits, but that's only because you just have more stuff. It's not because there's more physics added in.
Professor, 1.77 times 10 to the negative 5 coulomb, that's a value for charge, right?
Yes, that's the charge of these.
Oh, okay. You're just saying that's the charge that's a capacitor 5. You labeled it as C5.
What's that?
Because you labeled it as C5 on the board. So
I'm just, because I don't, you know, you got to give these things names. So
yeah.
for me, I should have said that. I just name them whatever the capacitor is. That's
okay.
the subscript.
Gotcha.
That's what that means. Yeah. Yeah, you got it. It's like you know, these problems become like a bit of a record keeping thing. So you have to work out those details for yourself, how you keep those records. And that's, you know, everybody's probably a little bit different, but that's how I do it. So there you go, Julia. Do you see it? Is it more clear now? So like once you work through it a couple times, then, you know, you see it. So you don't have to like work through all that. But then once you prove it to yourself, then you're convinced that, yeah, if the capacitors are the same, then that means that it's going to draw the same amount of charge in each one. And so then you can save yourself some time just by, you know, cutting it in half or depending, whatever the combination of capacitors are in that link is what I call it, then or that chain. If they have the same capacitance, then you know the charge will split evenly. Amongst them. That makes sense. Okay, yeah. Okay. Right. Okay. Why don't we go to break? What I'm going to do is you can have a working break. I'm going to just give you the answers for these other two, and you can work them out. And you know, at home, or you can fill out your notes. And if you have any questions about them, of course, you can always ask me. So for this guy, we've got the equivalent capacitance. So C Q is equal to 0.96. I guess it's 266, so it should be 0.97. I think it's 0.96 repeating, but whatever. Microfarads. And Q2 is like 7.7 microcoulombs. Q4, 7.7 microcoulombs. Q2, 4.4 microcoulombs. And Q3, 3.3 microcoulombs. Interesting. Somehow I don't have the charges for these guys. CEQ for this guy is going to be 4.8 microfarads. Doesn't look like I worked out the answer. The charges on that one. Sorry. 1, 2, 3, 4. Yeah, it doesn't look like I did, but you can work through it. So, you know, with this is again, it's kind of straightforward too, right? Like once you kind of get there, these two are in series, so you add those and then you redraw it, and all of that will be in parallel with that, and then you get those, and all of that is in series with that. You add those, and then all of that will be in parallel with that. And then the last two are in parallel, and you get the equivalent. So it's just, and once you get it, then you just start to, you know, you get the equivalent capacitance, get the charge on that equivalent capacitance, and then you piecemeal going back through all those pictures. Yeah. Sorry, I don't have it. I'm sure I worked it out. I guess I just forgot to write the answers in my notes. I know I have old notes. I worked this made these things years ago, so I worked it out. But if you have a problem, just let me know.
The answer you gave it for number 4?
Yeah. This is this guy.
Okay.
I'm confused why you wrote like 2 Q2s. Like, I'm confused which ones you're referring to for the answers for number 4.
That's because I left out one. Sorry. There's a capacitor over here. I'm bad. Sorry about that. Thank you for pointing that out, because that would have been very confusing. There's a capacitor over here that I called Q4. So I made it 4 microfarads. Thank you for that. So this is 4.0 microfarads. Bring the battery over here. So there's 4 different types, 5 capacitors with 4 types: a 4 microfarad, an 8 microfarad, 2, 3 microfarads, and 1, 2 microfarad up here. Is that better?
So are
This
there
is
supposed
Q.
to be 2 Q3s or 2 Q2s?
This right here?
Yeah,
Right
because you
here?
wrote Q2 twice for the answer key. Like you wrote
Did
2
I?
Q2s.
Huh. Did, didn't I? Oh, that's, guess one of those is Q8. Yeah. And I don't actually remember which was which. It would have to be this guy. Yeah, this has to be Q8. This has to be Q8. And this is Q2. About that before. Thank you, Julie. doesn't mean I screwed up on my students in the past. Well, I definitely know the numbers are right. If somehow you get some things turned around, then it'd be a challenge for you to figure it out. But I'm pretty sure. The reason I know is because you can see how it's got to add up, right? All of this is, I can figure it out back, kind of extrapolate, because all of this is in series with these two things. But capacitors in series have to add, right? Sorry, capacitor in series is the same charge. So yeah, capacitor in series, whatever. These are in series, let me say it again. These are series. So that's in series with that, and those two are in series with this whole combination when you redraw it. But capacitors in series have the same charge on them. So you can see from these two that these two capacitors should have the same charge, and you see it Q8 and Q4. Now, all of this has to have that same amount of charge, 7.7. And when you look at how these split, 4.4 plus 3.3 is 7.7. So I'm pretty sure that this is going to be 8. I'm absolutely sure about it. So it makes sense. So, but good catch, though, because that would have been probably that would have been very confusing. Thank you. All right. Are we good for the break? Any questions before we go on break? Let me see if I can, because I want to use my phone. Tell me if you can see the board okay from this thing now, from this second camera. Is that okay? I need to adjust that because I'm going to turn my phone camera off probably. Do I get with the board? You need to see it. Yes, no?
Yeah, I can see it.
Okay. All right, cool. All right. Okay, so let's take out time. We're a little bit over. Okay, cool. All right, we can get through this pretty quickly. We can get through this chapter in an hour because we have essentially already started talking. I've basically already built it up for you. I covered essentially the reason that charge will move in a circuit when we were talking about capacitance. And if you notice in the book, I don't think they really gave you that kind of discussion there about, the whole thing that, we talked about where, then now, I mean, you can talk about a little bit, but I kind of went a little bit further, I think. There's a potential hill that builds up, the positive charge rolls down this hill, negative charge rolls down this hill, but they kind of work together because there's really no positive charge in the first place, right? So the potential, the voltage is energy per unit charge. And so that's what gives and again, water is one of the best analogies, excuse me, that I think we have in terms of, that's why I keep going back to it, is a stream, water in a reservoir at the top of a stream, or even a water reservoir. When you look out at the, can I see one from here? If you go up into the Hollywood Hills, up into the Griffith Park, occasionally when you're walking around those trails, you'll see the reservoirs, big water reservoirs up in those hills there, and that water. It's usually at the highest level of the highest hill, because it's basically the water pressure it's simple. It's just gravity. The water pressure in your spigot in your homes and apartments and things, it's in part. I mean, you can put water pumps in certain
water circuits, but basically to save money and to design it properly for whatever community you're supplying water to, you put the water reservoir above all the houses, and essentially just potential energy of the water causes it to run down and creates the water pressure in the pipes. So that's why all those water reservoirs are up there in the hills if you've ever walked up there. But if you were to visualize, I like still just the basic example and analogy of, you know, a lake or some sort of water in a mountain range, and you know the water flows downhill after a stream or flows toward rivers or streams and then flows downhill. So in that case, the potential hill is literally the gravitational potential hill for the water molecules. And as I've said, the equivalent for that in the circuit, in a simple circuit, is the battery supplies the potential hill that the charge rolls down. Now, we can also make an analogy between the water molecules and what they encounter in their respective rivers as they roll down. Yeah. Essentially, there's a gunk, you know, in the river, right? Like even if there's not gunk, right? Even if there's not trash or whatever in the river, or, you know, just the sides of the river is not water molecules. It's actually the bank, you know, the banks, and also the bottom of the riverbed or the lake bed, riverbed, I guess. You know, it's dirt, it's sand. And when water rolls over that, there is resistance, right? There's friction, and that friction retards the motion of the water molecules. It kind of translates up, you know, in levels of the water. And also there could be stuff in the water as well, right? There could be, you know, sand built up, floating up. There could be leaves and rocks and wood things, you know, at various places. And usually there's more of that, more resistance along the sides than along the bottom. I'm sorry, along the sides than in the middle. So along the more resistance along the banks and the riverbed than there is in the middle of the river where there's just usually water. And so reasonably, logically, you can see when you stand on a riverbed that the water flows fastest in the middle of the river at the top, the middle top of the river, where there's less stuff to retard the motion of the water molecules, less resistance. So what we'll see is that within a circuit, we can define resistance of the charged particles rolling down their potential hills analogously. And we actually have a pictorial representation of that, right? Because I won't draw it again. You got a couple of places in your notes where we started off with the Einstein model of a solid that Einstein presented to the world in the, you know, around 1903, 1905, whenever he wrote that paper. And then we built on top of that, of all of the discoveries and theories, excuse me, that came over the next 20 years. Between, I guess it's probably like 30 years, between 1895 and 1925 is when modern physics was developed and ultimately led to quantum mechanics in 1925. And so we kind of built on top of those models. But the atom, I mean, the model of a solid that I kind of put together, compiling on top of Einstein's picture, we pretty much had that down by about 1912, 1915. And so if you kind of imagine that, right? So, and we know the only difference in that basic model between a conductor and a non-conductor is that the non-conductor has only the bound charge of the electron clouds around its atoms, but the conductor has the bound charge, but each of those atoms gives up an electron. So there's like a sea, it's called the Fermi sea, or the conduction sea, where there's literally a sea of electrons that whenever there is no battery in a metal, they just kind of hang out. It's like water in a lake, right? and they shimmer. They have their random motion, which would be kind of like if you're out on a looking at a lake on a relatively calm day, you might see some shimmer of water on top of the surface because of air and currents and things, but not a whole lot of activity. Just water is not stagnant, even though it may not be collectively moving in a particular place. That's kind of what the free electrons are in the wire of a circuit before you put a battery in or before you close the circuit. But the minute you close the circuit, it's like if that water were a dam, lake dam, then you open the gate and the water starts to flow downhill again. So that's what a battery does for the free charge. And the resistance is going to be all the stuff, the riverbed, the bank, any junk in the river that causes in any way and even the charges themselves, like they actually give resistance to one another because they're rubbing against one another, if you so to speak, as they move. And they still have that because they still have that random motion. It's more like, but then there's what we call a drift velocity is superimposed on top of the random motion. So if you were to visualize charge flowing collectively, which is ultimately what first thing we're gonna define is current. But I do want to give like a backdrop. We'll talk about second or so topic we'll talk about in this chapter. So random motion, I hope you read that somewhere, that terminology that I'm using. So this free charge in metal, they're not just sitting there, right? It's random motion. Think of like you might think of those water bugs, not a roach now, but like if you ever seen seen stagnant water like at a lake or something, and they have these, I forget what the name of these, I'm not a biologist, maybe some of you know, like these bugs that are on top of the water and they kind of dot around, eating stuff, I guess, I don't know. That's kind of what the random motion of a charged particle in a metal looks like. It's just like kind of has just this kind of random motion where it's kind of shooting around all over the place. But the thing is, when there's no external field, the average value of the position of the particle doesn't change. It's right in the middle. So even though it has this random motion, it doesn't really translate. It's all about some average position. Right? But as soon as you, and I've drawn the picture before, I won't draw it again, I want to move it forward, but you put the battery, so this is like the metal, the wire of a circuit. That's where the free charge is. Remember, the battery doesn't put charge into a circuit at all. All it does is create a potential hill, and then when the charge flows down the hill and gets at the bottom of the hill, the battery puts it back at the top of the hill. It doesn't put any charge, there's no influx of charge into the circuit from the battery. That charge, free charge, is in the wire. And again, as I said, it has this random motion. And the average value of the position is 0. But when you put the battery in and flip the switch, in the wire itself, it now sees an electric field. In the cross-sectional area, cutting through the cross-section area of the wire. So now this charge, it still has its random motion, but because there's an electric field, we know that positive charge moves in the direction of electric field. So if this were a positive charge, that random motion is still there, but if you look at it over time, what you see is there's a drift of the average value of that position of that charge in the direction of the field. All right. So where once the average value of the charge was not moving, now it actually starts to move, and with what we call a drift velocity in the direction of the electric field. So the random motion is still there, but it's kind of like it shifts along the direction of the field. And that is ultimately the reason that when all the positive charges or all the negative charges do that, along that particular direction, then that is what we call current. Current is the collective motion of the average value of individual charges along some average velocity, because even the drift velocity of each charge isn't necessarily the same, because they're right there, they're hitting different, it's not, but we deal with this kind of physics. It's like we're dealing with averages. Macroscopic physics is really about assuming that on an average value, all of the particles are behaving the same way. So that drift velocity leads to current, and current is essentially defined as the collective motion of free charge or collective motion of charge in a particular direction. And so this drift velocity, going back to the analogy of the water flowing down a mountain river, or maybe water leaving a dam, this drift velocity is actually the average, would be like the average value. I'm sorry, the drift velocity is the average value of the charge, but it would be analogous to the velocity of the water of the river as it flows down a particular direction. All of those water molecules, if you look at them individually, they don't necessarily have the same velocity, right? One part of the river might be flowing faster than the other, as we just mentioned, but the average value is what you would consider to be the value of the velocity of the speed of the river. And so that's how current is defined. And if you look at a cross-sectional area of the wire, right? All right, so that's the cross section. Remember, I'm just blowing this. This is connected to a circuit, so maybe somewhere I've got a battery connected to this thing somewhere. I'm just kind of blowing up the wire, looking at it there. So yeah, you got free charge in the thing, right? And we can follow a hole or and remember, a hole is just the absence of a negative charge. So you have the negative, the only thing that moves is the free electrons, the negative charges. So if you have a negative charge that moves to the left, then that's by charge conservation, you have an absence of a negative charge or a positive charge, a hole moving to the right. And as physicists, we happen to define current in the direction of the holes for some reason. I don't know. I don't really know the historical background of that. I think because there's an issue where I think Ben Franklin was actually the one that had name charges. He was one of the first. And I think there's an argument that we've misnamed him. That the positive charge should be the negative charge and the negative charge should be the positive charge. I don't know. I haven't really ever read the details of that in any science book. It's only been in like history books and things. So I'm not quite sure what the deal is with that. But anyway, engineers define current in the direction of the actual thing that's moving, which is the negative charges, and we do the holes. By the way, I don't think you're going to see that terminology hole, HOLE, in your book, but anyway, it's true. I'm not just saying that there are no positive charges moving. What else? I was going to say something. Oh yeah, so now we can define what current is. We can define it. Quantitative. This is a qualitative definition, but quantitatively. Oh yeah. So I wanted to say we define the current relative to the cross section of the wire. So the cross section, wire, if it has a cylindrical shape, the cross section area is just like, it's just a circle, right? It would have a area of pi r squared, just the area of a circle. So it's this face that charge is going through. And so we define current if you were to look at a cross-sectional area of a wire and calculate the number of positive charges going through that cross section in a particular unit of time, that is essentially how current is defined. It is the current, I is a symbol that we use, is the well, it's a symbol, capital I is what we use when we're implying that it's a constant current, a direct current, meaning it's not changing in value. It is a amount of charge, delta Q, going through a cross-section area of a wire in a certain amount of time, delta T. Yeah, that's it. So that's it, three equal signs, definition, current. Current has, its units are amperes, named after a French physicist, I think, Ampere. Forget his first name. And the capital A because it's proper name. And just looking at the units here, an ampere is a coulomb per second. So an ampere in an MKS system is coulomb is capital C, seconds S, units. Current is a scalar quantity. It doesn't have a direction. Scalar quantity. What else? It can be described also qualitatively as the rate at which charge flows through a cross-section area, another rate of flow. And that's a hint because the term rate in physics or in anything really is always a certain quantity per unit time. So it's the amount of charge per unit time. Yeah, and although, as I said, the only thing that's actually moved, I say this over and over again because embarrassingly enough, I think I might have been like a senior as an undergrad before I realized that there were no positive charges moving. I don't know like why it's, yeah. Yeah, I don't know. So I just don't want to make sure that you don't get out of general physics thinking that there's positive charges moving in the metal. I mean, translating. There's certainly the atoms are vibrating, but not translating. And it's just, again, it's, negative charges move, flow. If we didn't account for the absence of negative charges moving in the opposite direction and treating them like quantities, then essentially what we would have is a violation of conservation of charge. Yeah. And you might also think that, again, because this is another nice argument, and the argument that I came up with earlier also justifies this, which honestly, ironically, I never really had a good argument for it. You might think, well, okay, if you have the same amount of positive charges and negative charges, and if current is defined as delta Q over T, and if positive charge and a negative charge aren't the same thing, how come there's not a 2 in here, right? How come there's not, right? Because it would make sense, like, like positive charges are not negative charges. And so again, what is the same question I was asking about the capacitor? What is the value of the current when you have that situation? Is it 0? Positive charges and negative charges cancel? Is it 2I? Twice the amount of the value of charge for each, type of charge per unit time? Or is it just I? It's the same question, basically. And the answer is the same answer. Well, because there's only one thing actually moving. There's only one thing that's actually real, and that's the negative charges. Right? So keep that in mind, because I'm sure at some point you're going to see some questions or something that kind of asks you about that or to explain that or whatever. and that's why. Yeah. Okay. Oh, second. Yeah, sorry. Yeah. That's abbreviation for seconds. So that's current, and those are the properties. Current definition properties. Cool. We good? Okay, so before we get back into talking about resistance, again, let me give you another. So that's the basic definition of current, right? That's what we have. Current is this guy. But we can look at it. We can define current in a different way. We can define current in the context of the drift velocity and properties within in the metal. We call it the microscopic view of current. This is the macroscopic, where, and again, it's an empirical formula. So it's one of those situations where I've talked about before. We saw it with capacitance. We saw it last semester with friction, with the coefficient of friction. Whenever you define a physical quantity based upon your empirical observations, you oftentimes come up with formulas that are practical and give you a result, kind of an overall result of I don't know any other word, from a macroscopic point of view of, it's kind of like the idea, what's that old saying, you don't get lost in the forest for the trees or something. I don't know what, I'm trying to, like, there's two views you can have of a forest. One where you're right in the middle of the forest and you're looking up and the trees every place, you can't see any place in front of you if it's a thick forest. The other view is like the bird's eye view, where you can see the lay of the land. This is like the bird's eye view of current. It's like you're outside the wire looking at the result and how that moving charge interacts with other circuit components. However, we can get inside the wire and get down inside and, looking at all the stuff around us as we're moving through the thing. That's what the microscopic view of current can give us, because it will actually give us the true dependence of current. What is the current actually dependent upon? Is it dependent upon the charge, and inversely dependent upon the time, or are there other things involved? So let's take this picture right here, and let's assume that we are this. We have the cross section area here, which I'm going to call A. I didn't write it down. Into A. And sure, we know the area is probably, we can write it as pi r squared. And we also know that we've defined a particular direct area as a vector. Excuse me. I don't really need to get quantitative here with that, but just to remind you that we can ascribe a particular, the direction is always perpendicular to the cross-sectional area. And positive and negative depends on, if we want to define a positive or negative, we can. But here we can just say that the direction of the flow of charge is the positive direction of the area if we want, I guess. But and we have a specific length through which this this charge is moving, and that would map out a volume associated with the direction of the flow of this charge. So if we kind of look at a length, some arbitrary length, then that length is going to be equal to the drift velocity that I was just pointing out to you, this guy here, times the time at which we're looking, this delta t. That's how much, like we're actually just looking at the amount of charge that goes through this cross-sectional area. But in a certain amount of time, the drift velocity times that time will give a certain volume of charge that has actually moved through that cross-sectional area. Might have to think about that a little bit, but basically that length is going to be equal to the drift velocity, V sub d, times the time, the delta t, that I'm considering for calculating the amount of charge that's flowing through the cross-sectional area that bounds that essentially volume that I'm have mapped out and of which I'm considering the charge within. Ouch. Everybody with me? So let me define a few quantities in this quick derivation here. The volume of this, let me just go ahead and, so if this is the length of, and I'm kind of looking at a volume that's bounded by cross-sectional area A, it might look something like that. So what I'm trying to say is I'm just looking at within this wire, this section of this wire, I'm looking at all the charges within that volume. And in the time delta t, all those free charges that were in that volume initially will pass through the cross-sectional area as it goes to the right. That's what I'm saying. Okay. And so that volume, so microscopic view of current. Microscopic view. So that volume will be equal to the cross-sectional area A times, and this is really a delta X, right? Delta X or delta L, where delta X is equal to the drift velocity V sub d times the time delta t, and we'll just use the speed. We'll call it's actually I'm not, speed is the magnitude of velocity, so I probably should refer to it as a drift speed because I'm not putting any vector signs there on it. I'm not. It's just the magnitude of that thing. That terminology is usually used because obviously the negative charge has a different opposite velocity than the positive charge. And again, so people really talk in terms of drift speed, not velocity, just for that reason. Because as I said, there are no holes, there are no positive charges, so there's nothing actually moving. So drift, this thing is actually a drift speed, DRIF, drift speed. Surely you could define it as a velocity, but it's conventionally referred to as a speed, as opposed to velocity for reasons I mentioned. Now, capital N is always going to be a number. It's like the number of charge within this volume, the actual number of free charges in that guy. A number of charge. But if we have a volume and a number, we can define a number density. And that is useful because small n is defined as the number density. It's the total number of charges within a particular region or volume divided by that volume, number density. So mass is mass per unit volume, while number density is actual, that's literally a number per unit density. So it would have units of 1/cubic meters. So then with this relationship, I could define N, the total number of charges within the volume, as the number density, small n, times the volume. Everybody with me? catch up for a quick second. So I'm going to substitute equation 1 into equation 5 for the volume. So we'll get that N, the number N is equal to the number density times the volume, which is cross-section area times the delta X. Yeah. Now, we'll leave that for a minute and come back and look at charge here. Now, you know, we have these individual charges here, right? The electrons and holes. And the total number of charge could be defined in, you know, we know that the elemental unit of charge is just E, right? So if we wanted to know the total number, the total amount of charge in this volume, we just add up all the charges. That is, the total charge Q within that volume is equal to the sum of all the individual charges Q sub I. Well, all the individual charges are just the total number of charges, and the value their values are E. So that's, you know, small e, that little small e, the elemental unit of charge. So the total number of charge in the volume is equal to the number of charges times the value of each charge E. But N is equal to equation 6. So the total charge then within, call that total TOT, within the volume is going to be the number density times times the elemental times the cross-section area times the delta X time. And in your book, you might not see, you might just see Q, the value. You could use a generic because, you know, you might group the charge differently. I don't know. Let me see what your book does. So they use small e. Yeah, it looks like they use E. Some books you'll see Q. I think this is E. Yeah, they use E because that is the value charge. So we'll use E. So times times the elemental unit of charge. What now? What am I doing? Just lost my train of thought. Oh, right, yeah. So, but we have a delta X, right? We have a relationship for delta X. So I'll substitute equation 2 down there into equation 8. So 2 into 8 is going to give me a second. What happened? 2 into 8, yes. So Q total equals N times A times X, which is the drift speed, times delta T, times the value, the elemental unit of charge, E. Okay, now what? Oh, so now all we have to do is divide everything by delta T. If we do that, the delta T over here cancels, and we end up with and when I say Q total, I just mean it's the amount of charge. Like in delta T, all the charge that was in this volume has now exited that volume and moved out of that volume. And on an average value, it's replaced by the same amount of charge in that volume. So that just keeps happening over and over and over again. And so, yeah, if you assume the same increment of time, delta T, which could be a second, then as long as the battery is the voltage is not changing, which means that the slope of the hill is not changing, then those charges will flow at a constant rate, meaning that they will, as the total amount of charge that was in the volume before I started my clock, as that completely flows out in time delta T, it's completely replaced by the same amount of charge. And then in the next same delta T, that flows out. And so it just keeps doing it. So the charge flows around consistently as a constant current. Constant. Well, when we say constant, it's steady state is the term that's used, because obviously the charge is not, constant implies maybe no motion. I don't know. Steady state is the term that's actually used, but it just means that the value of the current is not changing. Anyway, divide by delta T, and that's going to be equal to N A V sub D, the delta T on that side are canceled, plus the elemental unit. Now, Gabrielle, what is this quantity right here on the left side? What did we just define that to be? Gabrielle, are you there? She kind of walked away. Rick Torres, are you there? What is this guy? Q over delta T. Okay. Hey, CL. Oh, did someone? Amabi. Everybody's walked away on break, trying to fool me. Anybody?
Current.
Is he?
Current.
Oh, yes, current. Thank you, Daniel and Julia. Opportunity. Yeah, current. It's just a current. Right? So that gives us another equation for current, but it actually gives us the equation that tells us what current is truly dependent upon. And if you look at it, you see it makes sense. So usually it's written like this: N number density, and then the drift speed, and then cross-sectional area. And it makes sense, right? That number density. Well, the current should be proportional to the number of charge per unit volume in the thing, right? You have less charge, and there's less stuff to flow. The value of the charge, that's not so obvious, but because it does contribute to the magnitude, you might think, right? Because we only have a certain kind of charge, right? But obviously, if the value of the elemental unit was larger, then because the current is proportional to the value of the charge, then that should increase as well. It's kind of hard to draw the analogy between a water molecule. You know, I don't know. You could talk about groups of water molecules as being the unit, but whatever. It's kind of hard to. It's more of a kind of a pedagogical thing, uh, example, as opposed to something that's realistic. Whatever, to get that. So obviously, the faster the water flows, the higher the current, that's your speed, right? And that's going to depend upon the voltage, the battery, and then the cross sectional area, right? If you have a wider river, there's more water to flow, right? Like if you close off the area through which the water has to move through, then it restricts the amount of water that can flow through that space. So the current should increase or decrease proportionally. So you would expect that you would have a proportional relationship between the value of the current and the value of the cross section through which it flows. So ultimately, then we have two equations for current: the definition of current, or the which comes from a macroscopic view, a bird's eye view of the current, and then you have a microscopic view, which gives you a more true dependence of the current, what is truly dependent upon relative to the wire. Oh. Oh. Hmm. Hmm. I should probably do one little thing here. Some books do this more than others, but this is probably the place to do it. And I hope I don't screw this up, because I don't actually have it in my notes. Oftentimes I don't really say something about this, but I'm gonna say something about it today, just so you don't get confused. Because in Halogen Resin, this is the first time I'm using Halogen Resin as a text. I haven't used this book since I was an undergrad. And so they have some slightly different things in it than the text that we used to use, which was the Zemansky text. So since it's there, I don't want you to get thrown off. Yeah. Mm. Remember, perspective is one of the themes of the course. And these quantities, you can look at them from slightly different perspectives about things. First of all, I want to tell you that your book actually uses a small I for current. I generally use, that's cool. I generally use the small I whenever I am talking about current that is changing, like it's dependent upon time. But your book uses slightly, so when I'm talking about a constant current, I usually do capital I, usually, and then small I of t whenever it's a changing current. So constant, for me, it's a notation. I usually use this for a constant or steady state. And then I use a small kind of cursive little I, and I usually put the time dependence in there whenever the current is changing. Your book does use a similar notation, although for the constant current, they just put a small I with no time dependence. I don't generally like that because a lot of times, you know, when we like in mechanics, when we were implying a time dependence, we use small things as well, but they didn't put a t in it. You know, like with the equation v equals v naught plus a times t. Well, that's a small v as well with its velocity, but what it really means is a v of t that they just didn't put the t in. So, you know, it just was kind of, this is something going back to undergrad where it was confusing to me that you meant a constant, you know, like but in most trig books, they will definitely always use it because they don't even deal with with change in current anyway. So usually there's no confusion for me. Well, capital I means constant, and you know, and usually I don't ever use this notation. I usually use this notation whenever I mean a change in current. So that's one thing. But the other thing is that this is just one version of a definition of current. You can define something called a current density, which is useful. And I just re-erased the picture, but it goes back to this picture where current density it's basically the amount of current per unit area, like the amount of current going through that cross-sectional area that I defined. So it's basically this thing divided by an area. So current density, and the symbol that's oftentimes used is a capital J, is actually a vector quantity. And its magnitude, which is just J, is defined as current, and I'm going to put as current per unit area. And its direction is in the direction of the drift velocity because it's a vector quantity. So when I write it as a vector, it's going to have a direction. Like if you look at this picture, the only thing in here that, well, A has a direction too, but that drift velocity, you know, it has a direction. It can be a vector. It's not just a drift speed, it's a velocity. So this current density will have the direction in the direction of the drift velocity. And so I don't know any way to write that as a, yeah, I don't know. Yeah, we just do the magnitude. Because whenever we can define this current, we can define the current in terms of two vectors, namely the current density in the area, and you see that like that. Like if you multiply through by A, then the current is going to be equal to, and it's an integral because, well, in most general form, it's equal to the current density J dotted into the cross-sectional area A. And that dot product is always going to be, well, it's usually zero. It doesn't have to be zero, but it's usually zero because in the wire, you know, the way I drew the wire, the direction that the current flows is always going to be parallel to the cross-sectional area, right? Like the current in a wire is always going horizontally, so it's always going to be going directly through the cross-section. So the direction of the current and the direction of the area are always in the same direction. So usually that integral then just becomes, you know, it's JA cosine of 0. So when you work out the current, it's just J, the current density, integral of the current density times the cross-section. But this current density it's a different perspective of looking at current, which can be useful. And your book just writes it down and gives you that. So that's something to know. Oh, and actually, you have to put a circuit to a loop on this because you're only going to have current flowing. The loop is the loop of the circuit. It's going around like a, you know, because you always have a closed loop whenever you do that. So they talk about that. So one other way to write this is in terms of current density. You can do that. Your book may do that. So it kind of gives you if I now divide through by the cross-sectional area, then what I have is current density, right? Because current density is I divided by A. So I can get the magnitude, or it's a way of writing current essentially as a vector. It's the way I think of it as current. So if I divide through by A, then what I have is I divided by A is equal to N E V sub D. But then I can write it as a vector because I can write the velocity as a vector. So I can say that J, which is equal to I over A, is equal to N E vector velocity. So it's really just the same equation, kind of, but just, gives me an opportunity to write the current as a vector, but then I have to write it in terms of its current density, really. Oh, so those are all the versions of current that you're going to see. Now, those are the useful versions. Okay, I need to take a quick break right now. Got to take some medication. So give me 5 minutes and I will be right back.
Yeah, Professor, your voice is lost. You don't have voice.
I was saying, yeah, I'm so sorry. I didn't realize that the hour went by so quickly. That class was over. So I would have just let you go before I went on break. So cool. Yeah, I will post those quizzes, Julie, you talked about, like for the chapters, even the last couple of chapters that we've done, and also the subsequent ones, and we can talk about how that's, how it's working for you over the next. When I see you on Wednesday, you can start working on those. I'll make them do maybe in a week or so, and keep working on the homework. I guess I should go ahead and assign homework from this chapter too, which will be due probably later next week. And yeah, so we got it rolling now, so with the homeworks, and so we'll put in some quizzes now, and then yeah. So go ahead and read the chapter. Go ahead and go through the next couple chapters too. So this is assigned this current and resistance, but then the next one on Ohm's law and Kirchhoff's rules. Just go ahead and start reading through that as you finish your homework up your homework on capacitors. All right.
Professor, I have a question. Do we have
Yes.
class on Wednesday?
What's going on Wednesday? There's
It's
a holiday?
Veterans Day. I was just wondering because I had heard from my friends that they weren't having any classes, so I wasn't sure.
Let me check the calendar. We might not. I didn't think about that. So if that's the case, let's make the test on a week from Wednesday then. Let me check the calendar. Class calendar, if you can ask questions. Degrees, divisions, where's the calendar? They changed this thing around. Oh my gosh. Calendars. Oh, academic calendar overview. Calendar. Academic year. General learning outcomes. Non-instructional days. So it'd be October 10th, would it be? Or November 10th? Let's see.
November
Or
11th.
11th. Oh yeah, you're right. November 11th, Veterans. That's a Monday. Oh, this is 2019, but it was last year, so it would be today. So where's the date? Where's this year's calendar? Let me go. It does. Last year it was, so I'm pretty sure it would be this year. Let me just make sure. Go try to find the right calendar. Oh man, why don't they have last year's calendar on here? Doesn't make any sense. Oh, I'm telling you, didn't update the thing. That's Slack. So frustrating. I guess it doesn't change. So yeah, if we had it last year, then we should be for this year as well. Certainly. Yeah, this was for fall and spring of last year, and they don't have it updated for this year. But so let's go ahead and make that. Let's go with that. So no class on Wednesday, I guess. So I don't really feel comfortable about having you come back into I want to kind of get a response on the quizzes and stuff before we, just can field the questions. Oh, and Julie, you had that question too. Do you have time after class, Julie? Or do you need to go now? Because I can.
For like the homework or
Yeah, for the homework.
Oh, I think we went over it like a couple weeks ago in class.
Yeah, because it's some of
I like the homework, but now since it's past due, I don't have access to the homework anymore.
This is for which? But this was for the homework on capacitance.
No, Gauss's. It was like I was saying like earlier in the chat, like some of it was hard, and then you were like, "Which one's hard?" And then I said, "Oh, that in particular, the last one in Gauss's law and stuff."
Okay. Oh, I got you.
Yeah.
So I see. So it was a homework on Gauss's law. Well, I can still go. Do you have time now, or do you want to?
No, I mean, I think we went over it a couple weeks ago, but now that the homework is past due, I don't have access to the questions anymore. So
what is the issue? Is there something that you need to discuss or with it, or?
I think I was just responding to your question earlier in the semester or earlier in the class, like, oh, how's the homework? And I was saying, okay, for the most part. And then I said some of the problems were hard or something. And then I said in particular, like the last one on Gauss's law, where we spent like half the class trying to figure it out, like or something. That's what I was talking about.
I see. But in the end, did you understand because I think we did figure it out.
I understood a little bit more, but it was still kind of hard.
Yeah, it's that graph. I remember it now. That graph was a little bit confusing, but we can go over it again. Oh, but I see you're saying you don't have access to it. I see. So
because the homework is past due now.
They still, yeah, but doesn't that just mean you can still see it, that you just can't? They won't let you submit anything for it. You can't even see the questions anymore.
I just tried to view the homework, but I could try again though.
So that was on Gauss's law. That was from chapter. Yeah. Yeah.
Yeah, it says like this assignment was locked on October 27th. So now I don't have access to the assignment anymore.
Huh.
It's locked because it's past due now.
Okay. Let's see if there's any way that I can.
But I mean, I wrote down like the problems, so it's not like the end of the world, and I could just, it's fine.
Did you take a look at the adaptive practice? Because they might have one similar to that in here.
I haven't yet, but I might later this week.
Let me see if I can quickly find something that might have one of them. And this was so what chapter was Gauss's law? Was it 23 or?
Yeah.
Okay. So what? Maybe it doesn't have questions. I can't see the questions. It just gives me an analysis of the students. Maybe I had assignment settings. When I go in, I don't actually see any questions. I just see the student activity inside here. I think I'm gonna have to fit. That's seems different than the way it was when it was now that I've integrated. So I have to look at that more closely. So it doesn't look like I can find any questions from that right now.
It's okay. I mean, there are similar questions like in the textbook, so it's not like the end of the world.
Yeah.
So, fine.
Yeah, those questions there are similar. You're right. It's just annoying because I thought it was just a matter of doing that. Tapping on it. What am I missing? Yeah, I don't know. Yeah, I'm gonna have to maybe find a video on something about how to access these problems in the adaptive practice. It's weird. When you go to the have you ever been to the adaptive practice? Have you clicked on that link within the assignments? They're all in there. If you go to the assignments and go down to the adaptive practice, when you click on it, what do you see? So
Well, when I did it, I kind of tested it out for chapter 13 like a couple weeks ago, and basically you just like when you click on it, it'll show you like it'll show you kind of like another screen, and then you click like begin or something, and then it'll just give you like a bunch of questions to answer.
I see. Yeah. So that's why I don't see that. I just see the results of people who've tried it. So it doesn't give me the questions. So maybe it's just set up that way. Okay. Yeah. All right. So I thought it gave me the questions before when it was a separate chapter, separate site. Okay. All right. Well, yeah. Over the next week, though, as you ask questions, you can text me and then we can talk Monday too. If but you can not text me, but email me questions, whatever, and I try to respond to specific things as you're going through when you're studying. And then we'll have one class day to meet before we have the test too. So I guess I should put out an announcement that there's no class because people are going.
Will the quizzes be due on the day of the exam?
Yeah, probably some of them because that's probably a good thing. give you a week to work on them. And the ones for this that you're not being tested on, I won't make those be due on Monday. So yeah. So I
But
guess go ahead.
the ones that we are tested on are, is it Coulomb's law and Gauss's law? Is that the first test?
Yeah, Coulomb's. Yeah, no gravity, just Coulomb's law and Gauss's law.
Okay.
Yeah. So I guess that's chapters 21 and 22. Yeah. Chapters 21 and 22. No, and 23. Right? Let me pull up the book. Assignments. Yeah, so, right, actually the 3 chapters, 21, 22, and 23. 21 is Coulomb's law, it's force. 22 is electric, because they break it up. Some people do that in the same chapter, and then Gauss's law is 23. Yeah. Okay. Hello?
Yeah, sounds good.
Okay. All right, cool. Cool. All right. All right, well. Be safe, and I will, guess I'll see you if there's nothing else. I'm gonna look at that right now, actually, see if I can get those out. Hopefully, if it'll be quick if I can have access to that information I had before that site. All right. Okay, see you next week.